Hello and welcome to Science Night Tales. I am glad you found this quiet space to wonder. Tonight, we are going to travel to the very edge of physics. We often think of space as a place of light, stars burning, galaxies spinning. But there are regions where the light stops. We are going to explore black holes, not as monsters that devour everything, but as quiet, profound objects that hold the deepest secrets of gravity and time. We will look at how they bend reality, how they shape entire galaxies, and why even these eternal seeming giants will eventually fade away. You do not need to understand complex equations tonight. You can simply let the mystery of these dark stars wash over you. The event horizon is far away, and you are safe to observe from a distance. If this perspective helps you feel a sense of awe in the unknown, you're welcome to like or subscribe. For now, let go of the day and let's drift toward the horizon together. Most people learn the word black hole before they ever learn what it actually is. They hear it in movies, in headlines, in jokes about things disappearing forever. A black hole is supposed to be loud, violent, a kind of cosmic disaster that tears everything apart. That image sticks, but it isn't how black holes usually behave. In reality, most of the time, a black hole is quiet, extremely quiet. So quiet, in fact, that for decades we didn't even know where to look for them. No flashes, no explosions, no warning sounds traveling through space. Just gravity, measured carefully, in small, precise motions of nearby stars. That difference between what we expect and what actually happens is where we begin. Not with impact, not with danger, but with stillness. Because despite the reputation, black holes are not defined by chaos. They are defined by rules. Rules that never change. Rules that can be written down. Rules that behave the same way every time, everywhere in the universe. And that's what makes them interesting. When astronomers talk about black holes, they don't start with destruction. They start with mass, with distance, with timing. They talk about how long light takes to travel near them, how clocks behave differently depending on where they are placed, how orbits stretch slowly, predictably. Nothing sudden, nothing dramatic, just physics doing what physics always does. If you were far away from a black hole, far beyond its immediate surroundings, you wouldn't notice anything unusual at all. Stars would still follow their paths. Gas would still drift through space. Light would still travel, one steady speed after another. The black hole wouldn't announce itself. It wouldn't reach out. It would simply exist, influencing its environment the same way any massive object does, only stronger, only deeper. And even then, that influence fades with distance. Gravity weakens smoothly, not sharply. There is no invisible boundary where everything suddenly changes. Just gradual shifts, tiny adjustments, measured over years, decades, centuries. So the fear we attach to black holes doesn't come from how they act. It comes from how little they reveal. We don't see them directly. We infer them from the way a star moves too fast, from gas heating up as it spirals inward, from radiation released before anything crosses the final threshold. The black hole itself stays hidden, not because it's aggressive, but because its defining boundary does not allow light to return. That boundary has a name, the event horizon. It isn't a surface you could land on. It isn't a wall. it's a location in space, a point where escape stops being possible. Cross it, and every future path leads inward. Not suddenly, not violently, just inevitably. But even that inevitability is calm. If you could observe from far away, nothing would appear to fall in faster and faster until it vanished. Instead, things seem to slow down. They stretch, their light becomes dimmer, redder, longer in wavelength. Time itself appears to drag. This isn't a special behavior invented for black holes. It's a consequence of gravity acting on time. A rule predicted long before black holes were confirmed to exist. A rule tested again and again, here on Earth, with clocks placed at different heights. Near a black hole, that rule becomes extreme. But it doesn't break, it holds. And that consistency matters, because it tells us that black holes are not exceptions to the universe. They are expressions of it. They follow the same equations as everything else, just pushed into ranges we don't encounter anywhere nearby. That's why the surroundings of a black hole are often more active than the black hole itself. The light we associate with black holes doesn't come from inside them. It comes from outside, from gas heating as it moves closer, from particles accelerating along magnetic fields, from matter interacted with matter before the point of no return. Once something crosses the event horizon, the show is over. No signals escape, no extra energy is released. From the outside, the black hole becomes simpler, not more complex, defined only by mass, spin, and charge. That's it. Everything else disappears from view. So instead of thinking about black holes as places where physics breaks down, it's more accurate to think of them as places where physics becomes very clear, unforgiving, exact, predictable. There are no surprises in how gravity behaves near them, only consequences, and consequences unfold slowly. Take time dilation. Near a black hole, time passes differently. Clocks closer to the mass tick more slowly than clocks farther away. This is not speculation. It's measured, calculated, verified. Near Earth, the difference is tiny. Near a black hole, it becomes enormous, but again, not abrupt. There's no moment where time suddenly stops. There's just a gradient, a smooth change from one rate to another. That smoothness is important. It means you can approach a black hole gradually. There is no instant where the universe suddenly becomes hostile. From the perspective of someone far away, the infalling object never quite crosses the event horizon. It just slows and fades and stretches. From the perspective of the object itself, nothing special happens at that boundary at all. No alarm, no shock. The physics locally still works. The same laws, the same structure, only deeper gravity and deeper time distortion. That difference in perspective is unsettling, but also reassuring. It tells us that black holes don't need to be loud to be powerful. They don't need to announce their presence. They reshape space and time simply by being massive enough. Nothing more, nothing less. Even Hawking radiation, often described as a dramatic effect, is anything but dramatic in practice. It's incredibly weak. For stellar mass black holes, it's far colder than the background of space itself. So weak that it takes far longer than the current age of the universe to matter. Again, no urgency, no threat, just a slow mathematical consequence our quantum rules applied to curve. to space-time. Black holes fade, eventually. Over timescales so long they are hard to put into words, and those timescales are key. Everything about black holes stretches time. Formation takes millions of years. Growth takes billions. Evaporation takes far longer than that. They are not sudden events. They are long processes. That's why supermassive black holes at the centers of galaxies are so stable. They've been there for most of cosmic history, quietly influencing star orbits, quietly shaping the flow of gas, quietly anchoring structures that last for billions of years. The one at the center of our galaxy is doing this right now. It isn't pulling stars inward in a rush. Stars orbit calmly, following predictable paths. Some come close, most stay far away. Life in the galaxy continues uninterrupted. The presence of a black hole does not mean destruction. It means order. A deeper gravitational well. Yes, but still governed by rules. Still measured. Still stable. So when we talk about approaching a black hole in this series, we're not talking about danger, we're talking about proximity, about how space behaves when gravity becomes dominant, about how awareness shifts as distances shrink, and we approach slowly, carefully, observationally. Nothing here happens all at once. Nothing needs to be rushed. Because the most striking thing about black holes, once you look closely enough, is how patient they are. They wait, they persist, they follow the same laws forever. And as we narrow our focus, moving closer to their immediate surroundings, we're not heading toward chaos, we're heading toward clarity, toward regions where gravity, time and motion reveal their structure with unusual precision, where the environment tells us more than the object itself ever could. So we begin not with the inside, but with the space around it. The paths matter takes, the way light bends, the gradual changes that signal we are drawing nearer. Nothing sudden, nothing overwhelming. Just a slow approach into one of the quietest extremes the universe allows. We don't begin by falling. That's important. When most people imagine getting close to a black hole, they picture a straight drop, a plunge, a loss of control. But that isn't how space works, and it isn't how black holes are approached. Instead, we begin at a distance. Far enough that nothing feels urgent, far enough that motion remains familiar. Out here, space still behaves the way we expect it to. Stars move along clear paths, gas drifts slowly, light travels in straight lines. The black hole does not dominate the scene. It doesn't announce itself. It exists, quietly, as one mass among many. What changes first is not motion, but measurement. Distances start to matter more, not up and down, not in and out, but how far, exactly, something is from the center. Around a black hole, distance is the primary language. Every effect depends on it. Every change scales with it. Gravity here is not a hand reaching outward. It's a field, a condition of space itself. And like any field, its strength changes smoothly. There is no edge, no sudden transition from safe to unsafe, just gradients. Gentle at first, almost unnoticeable. From far away, a black hole behaves like any other object with mass. If the sun were replaced by a black hole of the same mass, the planets would continue their orbits almost unchanged. Earth would still circle once per year. Seasons would still pass. Nothing dramatic would happen. That idea alone unsettles many assumptions, because it tells us that black holes are not defined by what they destroy, but by how mass shapes space. So as we orient ourselves here, the focus is not on the black hole itself, it's on the space around it. On paths, on balance, on motion that remains stable. Stable orbits are possible, very stable. Matter can circle a black hole for millions, even billions of years. Stars can loop around supermassive black holes at the centers of galaxies without ever getting closer. Their paths repeat, predictable, measured. Astronomers track these orbits with extraordinary precision, not because they're dangerous, but because they're reliable. The black hole becomes a reference point, a fixed mass anchoring motion around it, and that anchoring effect is calm. Nothing accelerates without reason. Nothing moves unless acted upon. Gravity does not yank, it curves. It changes the geometry of space, and objects follow that geometry. They move along the straightest possible paths within a curved environment. From this distance, those paths look familiar. Ellipses, circles, long, looping arcs. There is no sense of descent, no sense of being drawn inward. Only the awareness that space itself is shaped differently here. That awareness grows slowly. At first, it's purely conceptual. You know the black hole is present because calculations say so, because stars behave in ways that require a large, unseen mass, because timing measurements don't quite match expectations unless gravity is stronger than usual. But visually, nothing appears extreme. Space looks empty, quiet, almost ordinary. And that's the point. Before anything else can be understood, orientation has to replace fear. You have to know where you are. You have to know how motion works here. You have to know that proximity does not mean loss of control. So we stay at this distance for a while. We observe. We let our expectations adjust. Because black holes don't reward rushing. They reveal themselves only through patience, through careful comparison, through noticing what changes and what doesn't. Gravity here does not act like a force pulling things inward. It acts like a condition that shapes how objects move if they choose to move. If something has enough sideways motion, it stays in orbit. If it doesn't, its path curves inward more steeply. Nothing is compelled. Everything follows from initial conditions. And that idea matters. It means that approaching a black hole is not about being taken. It's about choosing a path. And paths can be wide, safe, long-lasting. As we continue observing from here, another idea begins to settle in. The black hole is not the center of activity. The surrounding space is. Most of what we learn comes from what happens around the black hole, not inside it. The way light bends slightly as it passes nearby. The way time ticks differently for clocks at different distances. The way orbits tighten gradually, not abruptly. These are subtle effects. They don't announce themselves. They require attention. But once noticed, they provide structure, a sense of order, and with that order comes reassurance. Nothing here is sudden. Nothing is hidden behind a trick. Everything follows rules that can be traced, step by step, outward into familiar space. So we hold this perspective. Distance first, orientation first, understanding before closeness, Because the next step is not falling, it's defining where the boundaries actually are. And to do that, we move closer, not in motion, but in definition. By narrowing our focus toward the regions where space itself begins to change more noticeably. As we narrow our focus, nothing new suddenly appears. There is no visible line, no surface, no boundary you could point to and say, it starts here. What changes is not space itself, but what can be known from it. This region is called the event horizon. The name sounds dramatic, but its meaning is very specific. It is not a wall, it is not a membrane, it is not a place where matter is torn apart. It is a boundary of measurement, a limit on information. To understand it, we don't think in terms of falling, we think in terms of light. Light is how information travels. Every observation depends on it. If light can reach us, we can know something. If it cannot, we cannot. Around a black hole, light still behaves according to rules. It always moves at the same speed. It always follows the geometry of space. As gravity increases, space becomes more curved, and light paths curve with it. Far away, those paths are nearly straight. Closer in, they bend slightly, then more noticeably, then sharply. At a certain distance, something precise happens. Light emitted outward no longer escapes, not because it is blocked, but because space itself curves inward faster than light can move away. At that distance, outward pointing paths loop back. Photons try to leave. They fail, not dramatically, not violently. They simply never arrive. That distance defines the event horizon. Nothing physical happens there. An object crossing it does not encounter resistance. There is no flash, no rupture. From its own perspective, motion continues smoothly. But from far away, something changes. Signals slow, light stretches, information fades. As an object approaches this boundary, the light it emits takes longer to reach distant observers. Each signal arrives more delayed than the last. Wavelengths lengthen, energy drops. Time, as measured from far away, appears to stretch. The object seems to slow down, not because it is actually slowing, but because information is taking longer and longer to arrive. Eventually, the signals become too weak to detect, not gone, just unreachable. This is why the event horizon is not a place of destruction. It is a place where communication ends. Beyond it, events may still occur, processes may still unfold, but no signal from those events can return. Not now, not ever. That is the limit, not of existence, but of observation. From the outside, everything inside the horizon becomes unmeasurable. From the inside, nothing special marks the crossing. Both descriptions are correct. They simply belong to different frames of reference, and that distinction matters because it shows that black holes are not defined by chaos. They are defined by perspective, by what different observers can agree on. The event horizon is where perspectives stop overlapping, where shared information ends, and this boundary depends only on mass and rotation. It can be calculated, predicted, mapped. For a stellar mass black hole, the event horizon may span only a few tens of kilometers. For a supermassive one, it can be larger than our entire solar system. Same concept, same rules, different scales. Nothing about the boundary is sharp in experience, only in mathematics, only in measurement, which is why we can talk about it calmly. It does not rush toward anything. It does not expand outward. It remains fixed unless the black hole gains or loses mass. Even then, changes propagate outward gradually, always within physical limits. So, as we linger here, just outside this boundary, the tone remains steady. We are not on the edge of catastrophe. We are at the edge of shared knowledge, and that realization reshapes how we think about what comes next. Because once information becomes limited, time begins to behave differently. Not suddenly, not theatrically, but in ways that are consistent, precise, and quietly profound. And that is where our attention moves next, not inward, but into how time itself responds to extreme gravity. Time does not change suddenly near a black hole. There is no moment when clocks stop. No instant where seconds stretch into something unrecognizable. The change is gradual, measurable, continuous. Time slows in strong gravity for the same reason light bends. Gravity affects the structure of space-time itself. That effect is not unique to black holes. It happens everywhere. On Earth, clocks at sea level run slightly slower than clocks on satellites. The difference is small, barely noticeable, but it is real. Near a black hole, the same effect becomes stronger, not different in kind, only in degree. The closer a clock is to a strong gravitational field, the more slowly it ticks compared to a clock far away. This slowing is not a malfunction. The clock works normally where it is. Each second feels like a second. Each process unfolds as expected. The difference appears only when clocks are compared across distances. One clock near the black hole, one far from it. Both correct, both consistent. They simply measure time along different paths through space-time. From a distant perspective, processes near the black hole appear slowed. Movements take longer, signals arrive delayed, rhythms stretch, but nothing locally feels delayed. No internal sense of dragging or resistance. The laws of physics remain intact. Chemical reactions proceed. Atomic vibrations continue. Time dilation does not pause existence. It reshapes comparison. This effect can be calculated precisely. The strength of gravity determines the rate of time. Distance matters, mass matters, rotation matters. Nothing is arbitrary. Near the event horizon, the difference becomes extreme. A second close to the horizon corresponds to many seconds far away, then minutes, then years. From the outside, time near the boundary seems to approach stillness. But this is not because time stops. It is because signals take increasingly long to escape. Information spreads thin. Arrivals grow sparse. From far away, the sequence stretches. From nearby, it remains intact. This distinction matters because it removes drama. Time dilation is not an experience. It is a relationship, a comparison between observers at different gravitational depths. It does not require falling. It does not require acceleration. An object could orbit steadily, remain stable, and still experience time differently. Even light itself is affected. Wavelengths lengthen as photons climb away from gravity. Energy decreases, frequency drops. This is called gravitational redshift. Again, gradual. Again, predictable. Nothing snaps, nothing breaks. These effects were predicted long before black holes were observed. They arise naturally from general relativity. They apply to stars, planets, galaxies. Black holes simply concentrate them. So when time near a black hole is described as slowing, it is not a warning. It is a description of geometry, of how space-time responds to mass. The closer you are, the steeper the curve. The steeper the curve, the greater the difference in time rates. Always smooth, always continuous. No thresholds, no shocks. Even crossing the event horizon does not mark a sudden change in local time. Clocks do not behave differently at that exact distance. Only distant observers lose the ability to track them. Time distortion becomes extreme, but never discontinuous. This understanding changes how black holes feel conceptually. They are not time machines. They do not trap moments. They do not freeze events in place. They create environments where comparisons stretch beyond reach, where shared timelines separate, and this separation is orderly, governed by equations, confirmed by observation. It allows us to speak about black holes without urgency, without alarm. Time near them is slower relative to elsewhere, that is all. And that slowing influences everything around them, not just clocks, but disks of gas, streams of matter, structures that remain outside the horizon. So from here, attention shifts outward again, away from time itself, toward the material that gathers nearby, the matter that circles, heats, radiates, not falling inward, but remaining in motion around the boundary. That surrounding structure is where gravity and energy become visible. Matter does not rush toward a black hole. It does not stream straight inward. What forms instead is a wide, rotating structure, an accretion disk. This disk exists because motion is conserved. Anything approaching a black hole already has velocity. That motion does not disappear, it redirects. Material spreads into an orbiting plane, circling again and again. From a distance, the disk appears thin, flattened, ordered. Each particle follows a path set by gravity and momentum. Nothing random, nothing sudden. The disk is not a surface, it is a region, a gradual arrangement of gas, dust, and plasma. Densities vary, temperatures vary, but the structure as a whole remains stable for long periods of time. Rotation dominates. Friction acts slowly. As material orbits, nearby layers move at slightly different speeds. Inner regions orbit faster than outer ones. That difference creates shear. Shear leads to friction. Friction converts motion into heat, not instantly, over many rotations, over long durations. As heat builds, the disk begins to glow, first faintly, then more strongly. Radiation escapes outward, light carries energy away. This loss of energy allows material to drift inward, very slowly, not falling, not plunging, drifting. Each inward step takes time, sometimes thousands of years, sometimes millions. The rate depends on mass, on composition, on the disk's thickness and magnetic properties, but always gradual, always governed by physical limits. Nothing in the disk moves faster than allowed. Nothing jumps ahead. Even near a black hole, the process remains controlled. The closer material gets, the more energy is released. Temperatures rise. Radiation becomes stronger. X-rays emerge, but this is still a process of balance. Energy in, energy out. Angular momentum redistributed. The disk adjusts continuously. It is not consumed all at once. Most of the matter in an accretion disk never reaches the event horizon. Some is ejected, some spreads outward, some remains in orbit for vast spans of time. Accretion is inefficient by design. It resists speed. That resistance is why disks last, why they shine steadily rather than flare briefly. Why black holes can remain active for millions or billions of years. The brightness we observe comes from this slow conversion. Motion into heat, heat into light. Not from the black hole itself, but from the material around it. The black hole does not radiate, the disk does. This distinction matters. It shifts attention away from the center, toward the surroundings, the environment. What we see is not destruction, it is regulation. Matter moving inward only as fast as physical laws allow. Even turbulence inside the disk follows constraints. Magnetic fields twist and reconnect. They transport angular momentum outward, allowing some material to move inward. But again, step by step, each process limited, each change incremental. The disk's structure evolves, but it does not collapse. From far away, the light appears steady, sometimes flickering slightly, sometimes changing over years. Those changes reflect adjustments within the disk, not sudden events, just long-term responses. This is why accretion disks are among the most reliable signals of black holes. They persist, they repeat, they obey the same principles everywhere, around stellar mass black holes, around supermassive ones, scaled by mass, slowed by size, but fundamentally similar. Understanding this removes urgency. The word accretion often suggests consumption, but here it means transfer, redistribution. Matter circulates, energy flows outward. Only a small fraction crosses the final boundary. Most of the activity stays visible, accessible, measured, and as disks rotate, another feature becomes possible. Not inward motion, but outward direction along the axis of rotation. A path where energy and matter sometimes escape, not as chaos, but as alignment, as structure. Those directional features extend far beyond the disk, and they form the next layer of the environment around a black hole. Jets do not begin as bursts. They are not sudden releases. They form gradually as a consequence of structure. Around many black holes, the accretion disk does more than rotate. It organizes magnetic fields. As material moves, magnetic lines are stretched and aligned. Over time, those fields become ordered along the axis of rotation, above and below the disk, along a direction where resistance is lowest. This alignment matters. It creates channels, not paths of escape driven by force, but regions where energy can move outward efficiently. The result is a jet, narrow, extended, stable. Jets are not streams of matter thrown randomly into space. They are guided flows. Particles follow magnetic field lines. Energy travels along those lines as well. Acceleration happens gradually. Close to the disk, speeds are modest. Farther out, velocities increase, approaching the speed of light only after long distances. Nothing erupts, nothing tears away. The process remains controlled from beginning to end. Jets persist because the conditions that create them persist. As long as the disk rotates, as long as magnetic fields remain organized, as long as energy continues to flow. Some jets remain active for millions of years. Some extend far beyond their host galaxies. Yet even at those scales, they retain structure. They remain narrow compared to their length. They remain aligned. This stability is a clue. It tells us that jets are not signs of instability. They are signs of balance. Energy produced near the disk must go somewhere. Some radiates outward as light. Some is carried away along these aligned channels. The black hole itself does not produce the jet. The disk and its magnetic environment do. This distinction keeps the focus on surroundings, on processes, on systems. Jets are often described as extreme, relativistic, powerful. Those descriptions are accurate but incomplete. They emphasize speed and scale, not order, not duration. In practice, jets are among the most consistent features we observe. They flicker, they vary in brightness, but their direction stays fixed. Their shape remains recognizable. Even when interacting with surrounding gas, the jet does not disperse immediately. It pushes gently. Over time, heating nearby material, changing its motion slowly. The effects accumulate, but never all at once. Relativistic motion introduces additional effects. Light emitted from the jet can appear brighter or dimmer depending on orientation. Time intervals can appear compressed. These are observational effects. They change what we measure, not what happens locally. Within the jet, processes continue smoothly. Particles spiral, fields guide them, energy transfers step by step. The term relativistic describes speed relative to light, not violence, not instability. Jets do not drain a black hole. They do not accelerate its growth dramatically. They are outlets, ways for excess energy to leave the system without disrupting it. In some cases, jets even limit further accretion by pushing surrounding gas outward, by heating it, making it harder for that material to settle back into the disk. This feedback is slow, regulatory. It unfolds across long spans of time. Observationally, jets help us locate black holes. They act as markers, visible across enormous distances. But what they mark is not destruction, it is persistence. A black hole system maintaining itself, balancing inward flow with outward release. The same principles apply at different scales. Around stellar mass black holes in binary systems, around supermassive black holes in galactic centers. The jets differ in size, in duration, in total energy, but not in nature. The physics remains consistent. Magnetic alignment, rotational energy, gradual acceleration, long-term stability. This consistency allows prediction. Models reproduce observed shapes. Observed motions match calculations. Nothing here requires unpredictability. Nothing relies on rare events. Jets can turn on, jets can fade, but they do so as conditions change, as disks thin, as magnetic fields weaken. The transitions are smooth, measured over years or longer, not seconds. Seen this way, jets are not interruptions. They are extensions. They belong to the environment of the black hole, part of the same system as the disk, part of the same long story. They carry influence outward, connecting the region near the black hole to space far beyond it. And beyond the immediate system, their effects blend into larger surroundings, interacting with gas clouds, with interstellar space, with the broader structure of galaxies. That outward connection shifts attention again from the near environment to larger scales, where the influence of black holes continues quietly across vast distances. At the centers of most large galaxies, something remains. Not active all the time, not always visible, but present. A supermassive black hole does not appear suddenly in a galaxy's story. It grows slowly, over hundreds of millions of years, sometimes longer. Material drifts inward. Gas clouds pass near the center. Occasional stars come close enough to be disrupted. Each contribution is small, spread out over time. The result is a central mass that increases gradually. Once established, it stays. Not as a controlling force, not as a commander, as a constant. The mass of a supermassive black hole is large compared to individual stars. Millions, sometimes billions of solar masses, but galaxies are larger still. Their stars orbit the center because of the combined gravity of everything inside. Dark matter, gas, stars. The black hole is part of that total. It does not pull the galaxy inward, it sits within it. The region where its gravity dominates is limited, measured in light days, light weeks, at most light years. Beyond that, the galaxy behaves the same way it would without it. Stars follow long, slow orbits. Gas clouds drift. Spiral arms maintain their patterns. The presence of the black hole does not disrupt this motion. It fits into it. From far away, the galaxy looks calm, rotating, structured, balanced. That calm persists even with a black hole at the center. Most of the time, supermassive black holes are quiet. They are not actively accreting large amounts of material. Their surroundings are sparse. Light from the center is faint. In these periods, the black hole's role is almost invisible. Its gravity remains, its mass remains. But nothing dramatic happens. These quiet phases last the longest, millions of years, often longer. Occasionally, conditions change. Gas flows inward, a disk forms, radiation increases, jets may appear. Even then, the activity is measured, limited by available material, bound by physical laws. Eventually, the supply decreases. The system settles again, back to stillness. This cycle repeats, not as a rhythm, not as a pulse, as a response. Galaxies and their central black holes evolve together, not in synchrony, but in correlation. The mass of the black hole tends to match the mass of the galaxy's central bulge. This relationship is not exact, but it is consistent. It suggests long-term interaction, feedback that unfolds slowly. Energy released near the center affects surrounding gas, heating it, changing how it moves. This can limit star formation in central regions, but the effect spreads gently, over time, across large distances. Nothing is forced, nothing is sudden. The galaxy adapts, the black hole adapts, both persist. Over billions of years, across cosmic history, even as galaxies merge. When two galaxies collide, their stars mostly pass by one another. Large separations remain. The central black holes approach more slowly. Over time, they form a pair, orbiting, losing energy gradually, eventually merging. This process takes millions of years, sometimes longer. The merger releases gravitational waves, ripples in space-time, measured far away. Yet even this does not disturb the galaxy dramatically. Stars continue their paths. Gas settles into new distributions. The galaxy reshapes. The central black hole remains, larger now, still stable. This persistence is key. Supermassive black holes are not episodes. They are features. Once present, they remain part of the galactic structure. Through calm periods, through active phases, through mergers and slow transformations. They provide a reference point, a center, not of control, of continuity. From our position, far from any galactic center, these processes are distant, abstract, measured through light that has traveled millions of years. What we see is not motion, it is record, evidence of long-term behavior, of systems that change slowly enough to be predictable. Even the most massive black holes follow the same rules as smaller Gravity scales with mass. Time dilation increases smoothly. Accretion depends on supply. Nothing breaks. Nothing behaves differently because of size alone. This uniformity allows understanding. It allows calm. Extremes exist within the same framework as everything else. Supermassive black holes do not dominate galaxies. They coexist with them. They influence without directing. They persist without demanding attention. At the center, they hold position. Around them, galaxies continue their long evolution. Stars form, stars age. Gas circulates. Spiral arms wind slowly. Elliptical shapes remain steady. Through all of this, the central black hole remains part of the background structure, present, stable, unremarkable in its consistency. This wider view shifts focus again, from individual systems to patterns across the universe, where black holes are not isolated curiosities, but recurring elements, repeating, embedded, quietly shaping the environments they inhabit. And from here, perspective expands further, from single galaxies to many, to the systems they form together, where black holes become one component in an even larger, slower arrangement. A black hole is often described by what it does to space, but just as important is what it does to time. Near a black hole, time does not stop. It does not break. It changes gradually, predictably. As gravity increases, time slows, not suddenly, not at a boundary, but continuously, step by step, as distance decreases. This slowing is not unique to black holes. It happens near any mass. Near Earth, the effect is small, measurable only with precise clocks. Near a star, it is larger. Near a neutron star, larger still. A black hole continues the same pattern, with no exception. The equations that describe time near Earth also describe time near a black hole. They are the same equations, applied across a wider range. This consistency matters. It means that black holes do not introduce new rules. They reveal the full extent of existing ones. When we observe matter orbiting close to a black hole, we are also observing time moving at a different rate. Clocks closer to the mass run more slowly. Clocks farther away run faster. Both are correct. Each follows its own local conditions. There is no single universal clock. Time is local. This idea feels unfamiliar, but it is not chaotic. It is structured, orderly, reliable. Near the event horizon, time dilation becomes extreme. From a distant perspective, processes appear to slow. Signals stretch, intervals lengthen. Yet for anything close to the black hole, time continues normally. Seconds remain seconds. Processes unfold at their usual pace. There is no sensation of delay, only difference in comparison. This makes black holes useful references. They define ranges where relativistic effects are strong and measurable. They anchor equations to reality, allowing predictions to be tested, confirmed, refined. Pulses from orbiting matter arrive later than expected. Spectral lines shift, orbital periods change. Each measurement aligns with theory, again and again. This repetition builds confidence, not excitement, clarity. Black holes do not distort time unpredictably. They stretch it smoothly, according to mass, according to distance, according to motion. All of it calculable, all of it consistent, even at extremes. This reframing changes how they are perceived. A black hole is not a threat to time. It is a reference point within it. a region where time behaves in a way that is usually too subtle to notice elsewhere. The laws remain intact, simply expressed more strongly. Over long durations, black holes persist. Their mass changes slowly. Their influence remains steady. This makes them stable markers across cosmic time. While stars evolve, while galaxies merge, black holes remain. They connect different eras. Matter falling in. Today may have originated billions of years ago. Light reaching us now left its source long before Earth formed. The black hole sits between these moments, not linking them actively, but allowing them to be compared. Time around a black hole carries memory, encoded in orbits, in radiation, in motion, all unfolding slowly, without urgency. From far away, these processes appear stretched, extended, yet they are not delayed. They follow their own internal rhythm, consistent with their environment. This teaches something subtle, that extremes do not require instability. That scale does not imply disorder. At its strongest, gravity still behaves. Time still flows. Physics still holds. Black holes become quiet confirmations of this. They are places where intuition fails, but mathematics remains, where imagination struggles, but measurement succeeds. This shift is important. It replaces fear with structure, mystery with framework. Not by removing the unknown, but by placing it within rules. Rules that apply everywhere, from the smallest masses to the largest, from weak gravity to the strongest. In this sense, black holes are not endings. They are checkpoints, markers along the continuum of space-time, showing how far known physics can stretch without breaking. As perspective widens, this role becomes clearer. Time near one black hole is one example. Across the universe, many exist, each with its own scale, each repeating the same patterns. Together, they map time itself, across galaxies, across billions of years, not dramatically, quietly, consistently. And from this understanding, attention begins to shift again, from individual clocks to the larger temporal structures they inhabit, where time stretches not just near objects, but across vast regions of space. Black holes are often introduced through moments. A star collapses, a core gives way, an event horizon appears, but once formed, almost everything about a black hole stops being about moments at all. What follows is duration. For most of their existence, black holes do not change in ways that are easy to notice. They do not flare constantly. They do not consume endlessly. They persist. A stellar mass black hole, born from the death of a massive star, can remain largely unchanged for longer than the time separating that star from the first multicellular life on Earth. Supermassive black holes persist even longer. They outlast the rearrangement of galaxies. They endure through multiple generations of stars, forming, aging, and fading around them. In cosmic terms, black holes are not events. They are conditions. This longevity shifts how they function in the universe. Instead of being active agents, they become reference points, objects whose defining trait is how little they change. Matter may drift inward, radiation may be emitted, but the central structure remains. Even the processes that do alter a black hole operate on timescales that are difficult for the human mind to hold. Hawking radiation is one such process. It is often described as evaporation, but the word can be misleading. Evaporation suggests speed. Hawking radiation is neither fast nor dramatic. It is a quantum effect arising not from the black hole itself doing anything, but from the structure of space-time at its edge. Particles appear and disappear. Very slowly, an imbalance occurs. Energy is lost. For a black hole with the mass of the Sun, this process would take far longer than the current age of the universe to complete. For supermassive black holes, the timescale stretches beyond most conceivable futures, long after stars have burned out and galaxies have thinned. In practice, Hawking radiation is not a mechanism of disappearance. It is a reminder of scale. On human timescales, black holes are effectively permanent. On stellar timescales, they are stable. Only on the deepest cosmic scales do they begin to change at all. This persistence alters how they interact with their surroundings. A black hole does not need to be active to matter. Its presence shapes orbits. Its gravity organizes motion. Stars near a galactic center move the way they do not because the black hole is consuming them, but because it has been there, unchanged for so long. Galaxies grow around these enduring centers. They rearrange themselves repeatedly while the black hole remains. In this way, black holes resemble geological features more than engines. They are like deep basins in space-time, features that define structure by existing, not by acting. The universe contains many things that happen quickly. Supernovae, collisions, bursts of radiation. Black holes are not part of that category. They belong to the background rhythm, the slow layer beneath visible change. Their long lifetimes make them anchors, not because they dominate, but because they persist through everything else that does not. As time stretches outward, activity fades, stars become rarer, energy thins, and still black holes remain, quietly carrying the memory of earlier epochs forward, unchanged enough to connect distant eras of the universe to one another. From here, the focus shifts again. If black holes persist for so long, the question is no longer what they destroy. It becomes how they relate to stars, to galaxies, and to the slow interactions that shape cosmic structure over time. When black holes do come together, it is rarely sudden. The word merger suggests impact, collision, a decisive moment. But in reality, black hole mergers begin long before anything meets. They begin with distance. Two massive objects separated by vast emptiness enter each other's gravitational awareness. They do not rush, they adjust. Each orbit is slightly altered. Energy is not lost violently, but gently, carried away in subtle distortions of space-time itself. This is in spiral, a slow, patient tightening of motion. For thousands, millions, sometimes billions of years, two black holes circle one another. Their paths become smaller, their timing becomes more precise, their presence becomes mutual. Nothing dramatic happens from one moment to the next. The system simply evolves. Gravitational waves emerge from this process, but even these are not explosive in the usual sense. They are not bursts of matter or light. They are ripples, patterns moving outward, carrying information about motion and mass. Most of the time, they pass through the universe unnoticed. They stretch and compress space by amounts smaller than atomic distances. They leave no scorch marks. They do not disrupt surroundings. They simply move on, From within the system, nothing accelerates toward chaos. The in-spiral remains orderly, governed by equations that change gradually as separation decreases. What makes this process remarkable is not its violence, but its predictability. Given enough time, orbital decay is inevitable. If two black holes are bound and nothing intervenes strongly enough, they will continue to lose energy. Their paths will continue to shrink. The outcome is not uncertain. It is merely distant. The final moments when horizons meet occupy only a tiny fraction of the system's total lifetime. They are not the main story. They are a brief punctuation at the end of a very long sentence. Even then, the merger does not produce debris. No fragments scatter outward. Nothing breaks apart. Two regions of space-time curvature resolve into one. The universe simplifies. What remains afterward is not evidence of destruction, but of continuity. A single black hole, slightly more massive, slightly altered in spin, settles into stability. This settling, called ringdown, is itself a calming process. Vibrations fade, distortions smooth out, the system relaxes. Again, inevitability replaces urgency. From a distance, the merger leaves almost no trace. Nearby stars continue their orbits. Gas clouds remain intact. The galaxy does not notice. Only space-time remembers, briefly, as waves pass through, carrying a record of the interaction outward at the speed of light. By the time those waves reach distant observers, the merger is already long over. The system has returned to stillness. This reframing matters, because it reveals that even when black holes interact, they do so within the universe's slowest rhythms. They do not interrupt cosmic order, they follow it. Mergers are not exceptions. They are extensions of long-term motion. Across the observable universe, countless such pairs exist. Some will merge in the far future, some already have. Most are still circling, patient and unchanged from one era to the next. Seen this way, black hole mergers are not moments of climax. They are milestones along trajectories that were set long ago. They remind us that the universe does not require urgency to arrive at outcomes. Time itself is enough. As individual interactions resolve, patterns begin to emerge at larger scales, across galaxies, across clusters, across cosmic history. Black holes do not sit at the center of galaxies as commanders. They reside there as participants. At the heart of many galaxies, supermassive black holes persist across immense spans of time. Quiet, massive, consistent. Their influence is real, but it is not absolute. Galaxies are not shaped by a single force. They evolve through many overlapping processes: gravity, motion, gas dynamics, radiation, time. Black holes are one part of this system. Their presence alters conditions nearby, not by issuing direction, but by responding to what surrounds them. Gas drifts inward. Energy is released outward. The exchange remains balanced over long durations. This is feedback. When matter approaches a supermassive black hole, it does not disappear immediately. It settles into rotating structures, heats gradually, emits radiation. Some of that energy flows back into the surrounding galaxy, not as an explosion, but as regulation. If too much gas accumulates near the center, radiation pressure and energetic outflows increase. They slow further inflow. Star formation nearby can pause or thin out. If gas becomes scarce, activity quiets, the environment cools, inflow resumes slowly. The system adjusts. This process unfolds over millions of years. Nothing reacts instantly. Nothing dominates permanently. Galaxies grow not because black holes command them, but because equilibrium is repeatedly restored. Observations support this quiet relationship. The mass of a galaxy's central black hole correlates with the mass of its stellar bulge. Not exactly, not rigidly, but consistently enough to suggest long-term coupling. Neither side controls the other. They evolve together. In some epochs, galaxies are rich in gas. Star formation proceeds rapidly. Black holes accrete more actively, releasing energy that gently reshapes the surrounding medium. In other epochs, galaxies thin out. Star formation slows. Black holes become quieter, persisting without spectacle. Across cosmic history, this cycle repeats, not as a loop with a clear beginning or end, but as a gradual modulation. The black hole does not dictate when stars form. It influences conditions under which formation becomes easier or harder. This distinction matters because it removes hierarchy. Black holes are not engines driving galaxies forward. They are stabilizers within systems already in motion. Their role is subtle. Their effects are cumulative. From far outside a galaxy, nothing about its shape announces the presence of a black hole. Spiral arms continue their rotation. Elliptical systems remain smooth and extended. Satellite galaxies orbit as they always have. Only near the center do traces appear. Changes in gas temperature, altered star formation rates, quiet signatures of long-term interaction. Even these are gentle. At no point does the galaxy lose its identity. At no point does the black hole become the story. Instead, both persist together. This perspective reframes influence itself. Power is not loud. Impact is not immediate. Change does not require urgency. Across billions of years, small adjustments matter more than sudden events. Black holes participate in galaxy evolution the way gravity participates in structure formation. Always present, rarely noticed, never absent. Their effect is not to steer galaxies toward a goal, but to keep them within stable ranges. Too much collapse is prevented. Too much dispersal is softened. Balance emerges. Seen this way, galaxies are not shaped around black holes. They are shaped with them. The relationship is ongoing, unfinished, unresolved, and it does not conclude here. Beyond individual galaxies, patterns continue among groups, clusters, and the large-scale web of matter itself. Black holes are not rare. They are not confined to distant galaxies or extreme moments in cosmic history. They appear wherever massive stars complete their lifetimes. Across spiral arms, the elliptical halos, irregular systems, stellar mass black holes remain distributed quietly, embedded within galaxies like long-lasting remnants. Most formed billions of years ago. Many formed long before the Sun existed. Others continue to form today, following the same physical pathways without variation. A massive star exhausts its nuclear fuel. Pressure decreases. Gravity continues. The outcome depends on mass, rotation, composition. But the process itself is familiar, predictable. No spectacle is required. For every black hole that captures attention, there are countless others that remain inactive, drifting through galactic environments, exerting gravity without interacting strongly with nearby matter. They do not announce themselves. They do not alter their surroundings noticeably. They simply persist. Surveys suggest that in a galaxy like the Milky Way, millions of stellar mass black holes may exist. Most are isolated. Some orbit companion stars. A few accrete slowly, emitting faint radiation. Many do nothing observable at all. This does not make them insignificant. It makes them typical. Black holes represent one of several stable end states for massive stars. Alongside neutron stars and white dwarfs, they form a quiet population of remnants that shape galaxies subtly through mass distribution rather than activity. Their gravity contributes to the overall structure of stellar systems. Their mass remains part of the galactic budget. Nothing more is required. Even when black holes interact, the interactions remain restrained. Binary systems evolve slowly. Orbital energy dissipates gradually. Our timescales stretch across millions or billions of years. From the outside, nothing appears urgent. On larger scales, black holes trace the same cosmic structures as galaxies themselves. They follow filaments of dark matter. They cluster where stars once clustered. Their distribution mirrors the history of star formation across the universe. Where stars formed rapidly, more remnants exist. Where galaxies aged early, black holes settled earlier. This pattern repeats everywhere. There is no special region where black holes dominate space, no boundary where they suddenly appear. They are simply part of the background inventory of matter. Even supermassive black holes follow this logic. Nearly every large galaxy hosts one at its center. Not because something extraordinary occurred, but because long-term processes favored accumulation in dense regions. Over time, smaller black holes merged, gas accreted, mass concentrated. The outcome became common. Once again, predictability replaces surprise. Seen across the observable universe, black holes are not anomalies interrupting cosmic order. They are products of it. Their formation follows from gravity and nuclear physics. Their persistence follows from stability. Nothing about them requires urgency to explain. This realization changes the emotional tone. When black holes are framed as isolated extremes, they invite fear or fascination. When framed as widespread outcomes, they invite understanding. They belong. They are part of the same continuum as stars, planets, and galaxies, linked by cause, governed by the same equations, distributed by the same large-scale structure. Even their invisibility fits this pattern. Most matter in the universe does not shine. Most mass does not radiate strongly. Black holes align naturally with this quiet majority. They do not interrupt cosmic processes. They settle into them. As observation techniques improve, more black holes will be catalogued, not because the universe is changing, but because measurement is refining. Each detection reinforces the same conclusion. Black holes are everywhere, and because they are everywhere, they are no longer exceptional. They are endpoints. They are records of past stars. They are quiet markers of what has already occurred. Nothing about their distribution suggests urgency or instability. Instead, it suggests continuity. At the center of every black hole, our descriptions stop. Not because something chaotic happens there, not because the laws of physics break into disorder, but because the tools we use to describe reality reach the edge of their precision. What we call a singularity is not an observed object. It is not a place we can measure directly. It is a result produced by equations when those equations are extended beyond where they have been tested. General relativity describes gravity with extraordinary accuracy. It predicts orbits, time dilation, gravitational waves. Its predictions have been confirmed again and again. But when gravity becomes extremely strong and matter is compressed beyond known limits, the mathematics produces infinities. Density becomes unbounded. Curvature becomes undefined. Time and space lose clear meaning within the framework. These infinities are signals. They do not describe physical chaos. They indicate that the model has reached the boundary of its applicability. In the same way that classical mechanics fails at atomic scales, current gravitational theory signals its limits at extreme compression. This distinction matters. The uncertainty associated with singularities is not disorder in nature, it is uncertainty in description. We do not observe singularities directly. No signal travels outward from within the event horizon, carrying information about internal structure. Everything we know about black holes comes from outside: mass, spin, charge. These quantities are measurable. They remain stable. They evolve according to known laws. The internal details remain inaccessible, not because they are violent, but because the structure of space-time prevents information transfer. This is an observational boundary. When physics speaks of unknowns here, it is not describing randomness, it is acknowledging incompleteness. Quantum mechanics offers possible extensions, so do candidate theories of quantum gravity. Each proposes different internal behaviors. Each removes infinities in different ways, but none are yet confirmed. This does not create urgency. It creates patience. Throughout scientific history, similar boundaries have appeared. Before atomic theory, matter seemed continuous. Before quantum mechanics, energy appeared smooth. Before relativity, time appeared absolute. Each boundary was not chaos. It was a prompt for deeper understanding. Black holes fit this pattern. They are not locations where reason collapses. They are locations where existing frameworks stop resolving detail. From the outside, nothing unusual occurs. Orbits remain stable. Time dilation follows precise formulas. Radiation behaves predictably. Even near the event horizon, space-time behaves smoothly for local observers. No signal marks a sudden breakdown. No turbulence announces a transition. The uncertainty lies entirely in regions that cannot be probed. This separation allows calm. If singularities represented physical instability, black holes would affect their surroundings unpredictably. They do not. If internal chaos leaked outward, observations would reflect it. They do not. Instead, black holes are among the simplest macroscopic objects described by physics. They are defined by a small set of parameters. Their evolution is slow. Their interactions are constrained. The unknown remains contained. This containment reshapes perspective. When uncertainty is framed as disorder, it invites anxiety. When framed as a limit of measurement, it invites acceptance. We can know where our knowledge ends without fearing what lies beyond it. The universe does not demand immediate answers. it continues regardless. Black holes existed long before humans formulated equations. They will persist long after current theories are revised. Their presence does not depend on understanding. This is not a failure of science. It is a description of its structure. Knowledge advances by identifying boundaries, not by denying them. In this sense, singularities serve a quiet role. They mark when new theories must eventually connect with old ones. They indicate regions where gravity and quantum mechanics must reconcile. But they do not disrupt the present order. For now, the observable behavior of black holes remains fully governed by known physics. Their growth rates, their radiation, their gravitational influence, all proceed without ambiguity. What lies inside remains unmeasured, and that is acceptable. Uncertainty here does not imply danger. It implies scale. The scales involved are far removed from everyday experience, far removed from planetary systems, far removed from biological time. They do not intrude. As observation continues, constraints tighten. Gravitational wave detections refine models. High-resolution imaging maps space-time near horizons. Each new measurement reduces speculation, not by revealing internal structure, but by confirming external consistency. This consistency is the dominant feature. Black holes do not destabilize physical law. They reinforce its reach. Where knowledge stops, order does not end. It simply remains undescribed. This understanding allows the narrative to soften. Black holes no longer appear as threats or exceptions. They appear as regions where current language pauses. They do not demand resolution, they allow continuation. And from this point, attention naturally slows. There is nothing left to explain urgently. No climax to reach, only long durations, long persistence, long silence. From here, the story does not conclude. It eases into repetition, into cycles, into timescales where change happens without pressure. And in that gradual quiet, the presence of black holes becomes just one more steady feature of an ordered universe, continuing without interruption. Gravity does not end where our attention fades. It remains. Not as a force demanding notice, not as an event unfolding, but as a steady condition that continues whether it is observed or not. Long after motion settles into repetition, long after light has traveled its measured paths, gravity continues to curve space in the same quiet way. Around black holes, this persistence is especially clear. Nothing new needs to happen for gravity to remain present. No matter needs to fall. No energy needs to flare. The field is already there. It has shape, it has strength, it has direction, and it changes only slowly. Time near a black hole does not stop. It stretches, it slows relative to distant clocks, but it remains ordered. Seconds follow seconds. Processes unfold in sequence. Cause still precedes effect. Even extreme gravity does not suspend structure. It rearranges scale. What feels dramatic in description is, in practice, gradual. Orbits persist. Disks rotate. Jets align along fixed axes. The system holds. Across millions of years, accretion adds mass in small increments. Across billions of years, spin adjusts by subtle amounts. Nothing here is hurried. This slowness is not emptiness. It is continuity. Gravity does not announce itself. It does not pulse or fluctuate without reason. It remains present in the same way night remains when clouds pass, unchanged by attention. As galaxies evolve, supermassive black holes remain at their centers, not as rulers, but as reference points. Stars form, live, and fade around them. Gas circulates, spiral arms shift. The black hole's gravity does not intervene. It does not guide. It does not command. It simply remains. Time dilation near strong gravity does not accumulate urgency. It accumulates difference. Clocks near the horizon tick more slowly relative to distant observers, but they do not feel delayed from within. Local time flows normally. Processes proceed without awareness of comparison. This is one of the quiet lessons of relativity. Extreme conditions do not feel extreme to what exists within them. They are simply local environments following consistent rules. From far away, the differences become measurable. From nearby, they are invisible. Both perspectives are correct. This layered understanding allows rest. There is no need to resolve every scale at once. No need to reconcile every reference frame simultaneously. Physics does not demand a single viewpoint. It accommodates many. Black holes do not compress meaning. They expand context. They show that the same laws apply across vast ranges of mass and time, that order persists even when intuition struggles. As Hawking radiation slowly removes energy, the process unfolds over durations far longer than any civilization. The radiation is faint. The change is negligible on human timescales. The black hole remains essentially unchanged, continuing its quiet interaction with the surrounding universe. This is not decay in the everyday sense. It is transformation stretched so thin that it resembles stillness. Even mergers follow this pattern. Two black holes orbit each other for millions of years, gradually lose their energy through gravitational waves. The inspiral accelerates only near the very end, and even then, the time scale remains measured. The result is not destruction, it is combination. A new black hole forms with predictable mass and spin, settling quickly into stability. The surrounding universe continues unaffected beyond a small region. Space absorbs the waves. Time resumes its local pace. Nothing lingers. Across the observable universe, countless black holes follow these same patterns. Stellar remnants scattered through galaxies, supermassive anchors at galactic cores. None of them are rare. None of them are exceptional in their behavior. They are outcomes of known processes. Their presence does not disrupt cosmic order, it confirms it. Gravity behaves the same everywhere, only scale changes. When attention moves away from spectacle, what remains is repetition. Mass curves space-time. Space-time guides motion. Time flows differently depending on gravity. These relationships do not vary. They do not require interpretation. They do not invite urgency. They simply continue. In this continuity, perspective softens. Black holes no longer appear as endpoints or threats. They appear as long-lived features in a universe defined by patience. Their silence is not absence, it is stability. Nothing about them rushes toward conclusion. They do not signal endings. They participate in cycles. Matter falls in slowly. Energy radiates outward gradually. Information remains conserved in ways still being understood. The details may evolve, the framework remains, and beyond any single system, beyond any individual object, gravity shapes the large-scale structure of the universe itself. Clusters form where mass accumulates. voids remain where it does not. These patterns stretch across hundreds of millions of light years, held together by the same interactions that operate near black holes. There is no separation between the extreme and the ordinary, only continuity across scale. This realization does not demand reflection, it allows release. Nothing needs to be solved right now. Nothing needs to be reached. The universe does not move toward resolution, it moves through time. Black holes are part of that movement, not as destinations, but as steady participants. As attention drifts, what remains is not mystery, but persistence. Gravity remains. Time continues. Change unfolds slowly. There is no final image to hold, no final statement to remember. Only the sense of structure continuing without instruction. The same laws operating without interruption, the same patterns repeating without emphasis, and in that repetition, it becomes easier to let go of direction, to rest in scale, to rest in duration, to rest in the quiet fact that even the most extreme objects in the universe obey calm, consistent rules. Nothing presses forward, nothing pulls inward. Gravity remains, and the universe continues, unchanged by whether it is being watched, settling into its long, steady rhythm, without pause, without conclusion.